Maybe I'll announce and then you come up and I give you. I know, I never know what to do. All right, everyone, we'll start the session in about 1 minute, so please take your seats. All right. Welcome to the DeepRL 3, I think. It is my great pleasure to introduce the first talk of the day, which actually got the ICML Best Paper Honorable Mention Award. The work is called Social Influence as Intrinsic Motivation for Multi-Agent Deep Reinforcement Learning by Natasha Jakes, Angelique Lazaridou, Edward Hughes, Chalar Gulcheri, Pedro Ortega, DJ Strauss, Joel Lebo, and Nando De Freitas. Please welcome Natasha Jake, who will present this work.
Congratulations. Oh, thank you. Hi, it's my pleasure to be here. I'm glad you guys could make it. So let's get right into it. We wouldn't be sitting in the DeepRL session if we didn't think that there's been some really exciting progress in DeepRL lately. But we also know that there's a problem. So a lot of the big successes in deep reinforcement learning tend to be restricted to a very specific domain. Generalization across multiple domains, even multiple related tasks, is still a really big problem. So one way to address this is to think about intrinsic motivation. So these are reward functions that could cause an agent to learn across many different environments. So some approaches to this have been something like curiosity, where the agent is driven to find novelty in its environment, and therefore it learns to explore and learn about the environment. Another approach is empowerment, where you reward the agent for having high mutual information between its actions and its own future state. So basically, it's driven to be able to manipulate the environment. So these are really cool, but when I look at this, I have to ask, what else motivates people? So are people only intrinsically motivated by a drive for novelty and a drive for power? I would say not. I think that people are actually incredibly motivated by other people. So for example, if you guys were looking at me, like this audience here, I would be very strongly motivated to go to the next slide. So I think social learning is incredibly important to human learning. And if you don't believe me, I've thrown up a bunch of citations here, which say that social learning is really important for driving human cognitive development and also driving cultural evolution. So we wouldn't be standing here talking about deep reinforcement learning if we didn't have really good cultural evolution, social learning, and transmission of ideas. So wouldn't it be cool if we could allow agents in a multi-agent RL framework to learn socially from the other agents? Now, there are many ways you could approach doing this. The approach we've taken in this paper is to do this by giving agents an intrinsic social motivation for having a causal influence over the actions of other agents. Now, why do we focus on doing it this way? Well, one thing is that if we can learn from only the actions of other agents, from only observing their actions, then we don't need to observe other agents' rewards. And we think that this is a bit of a more realistic assumption if we consider downstream applications like autonomous driving. So it's pretty unlikely that Tesla is going to share its proprietary reward function with another car that was made by Waymo. So wouldn't it be cool if these agents could learn from the other agents in the environment just by observing the actions that they actually execute in the environment, like turning left? So that was the motivation for doing it on the action level. And the reason we focus on this as well is we'll show later that giving this causal influence reward is equivalent to rewarding the mutual information between agents' actions. And so we have this intuition that rewarding this mutual information will be an inductive bias that drives agents to learn coordinated behavior. So how do we actually do this? Well, let's start with our standard RL agent. It's got some convolutional layers and LSTM. It's outputting a policy. And then we're going to equip it with a second network that's going to predict the actions of other agents. And we're calling this a model of other agents. So essentially what we do is we allow the agent to observe a bunch of trajectories of the other agents acting in the environment, and then it learns, just with supervised learning, to predict the actions of every other agent at the next time step, given the actions at the current time step, including the agent's own action. So what this allows it to do is to simulate counterfactual actions that it could have taken and run that through its predictive model to understand the effect of its own actions on others. So essentially, this gives the agent the ability to ask the question, what do I predict this other agent B would do if I had taken a different action at this time step instead? So this allows us to do the following. So the agent can sample a bunch of counterfactual actions from its own policy at time step t, run that through its model of other agents, its predictive model, understand the predictions for what the other agents would do given each of the counterfactuals, and then sum over that. And that allows it to derive basically the marginal policy of another agent. So basically, agent B's policy if it wasn't considering the action of agent A. And the divergence between that default policy of agent B and agent B's policy conditioned on agent A's action is a measure of the causal influence of agent A's action on agent B's action. And if you don't believe me that it's the causal influence, that's what this complicated diagram is here to show. So if you're familiar with Pearl's understanding of causality in Bayes nets, we know that causality can't pass through this collider node here or here. So there's no backdoor path between A's action and B's action at the next time step. And we can say that this is the causal influence of A on B. But regardless of that, the big idea is to give this as a reward to agent A. So agent A gets a reward for taking an action that causes B to change its intended action. And we show that this is related to the mutual information. So you can see the formula for the mutual information here. It requires summing over the probability of the state, etc. But as we sample a bunch of random trajectories from the environment, and we take the expectation over those trajectories, then we can see that in expectation, the influence is actually just the mutual information between agents' actions. So if you recall, I mentioned that empowerment is the mutual information between an agent's action and its future state. So here, we're thinking of this as kind of a novel form of social empowerment, where we're rewarding the mutual information between agents' actions. So I'm going to stop here because there's a really common question that I get. There's a kind of a hiccup with this influence reward. Does anybody have an idea what it is? I don't know if you have the ability to ask a question right now. Okay. So one issue with this is that influence on another agent doesn't always have to benefit that other agent, right? It might be possible to influence another agent in a way that doesn't help them. So maybe I just get in that agent's way, it causes the agent to have to change its path around me, but I haven't helped them. So we take two approaches in this work to address this. And the first is to test this in environments where achieving cooperation is exactly the hard problem. So these are these sequential social dilemma environments. And you can think of them like a spatially and temporally extended prisoner's dilemma. So the first environment is called harvest. Agents are trying to harvest these delicious apples, but if they harvest them too quickly, the apples become depleted and don't grow back. So each agent is greedily motivated to harvest as many apples as it can, but if they all follow this greedy strategy, they all lose. Similarly, in cleanup, agents try to clean the river in order to make apples appear, but both environments are partially observable, and in this one, when the agent is cleaning the river, it can't even see the apples, and it doesn't know that it can be easily exploited by other agents harvesting those apples. So these are very difficult problems for RL agents, and to make that a little more concrete, what we're looking at here is a shelling diagram. And what this is showing is the payoff in terms of reward that each agent can expect to receive if it follows a defecting or exploitative strategy, that's shown in red, or a cooperative strategy, as shown in blue, given the number of other agents that are cooperating with it out of 5. So essentially here, all the other agents are cooperating. Here, everybody is defecting. And as you can see from these diagrams, an agent is always expected to get a higher payoff if it follows this defecting strategy, so it would be greedily motivated to defect. But of course, if all agents do that, they all get very low reward. So this type of long-term reasoning over these repeated interactions is really difficult for a vanilla RL agent to solve, and even if you put a state-of-the-art architecture like Impala on it, it really can't solve it. But we see that if we give the agents this influence reward, it actually improves their ability to cooperate in these environments. So what you're looking at here on the y-axis is actually the collective reward obtained by all of the agents together. So the agents are only trained on their individual selfish reward, but when we give them the influence reward as well, we see that they obtain higher group outcomes, which is evidence that they're cooperating in these environments. And even more encouraging, we see that the performance actually exceeds that reported in prior work, where agents were actually able to observe each other's reward functions. So this was this inequity aversion work, where agents didn't want their reward to differ too much from the group average. And so we see we're doing a little bit better than that, so that's exciting. But this doesn't really answer the question of how the influence reward is actually helping these agents to learn to cooperate. So let's dig into that a bit. So what you're seeing here is a trajectory in which this purple agent is the only one that's been trained with the influence reward. And you can see that it's behaving a little bit differently than the other agents. So when there's no food, the other agents continue to move around and explore on the map in search of apples. But in contrast, the purple agent holds still. And in fact, it's learned a policy where it only ever moves on the map when there are apples or food present. So why did it learn to do that? Well, let's take a look at a moment where it actually gained some influence over another agent. So here's a moment where it had influence on this yellow agent here. And if you remember, the environments are partially observable. So this agent can only see what's in this red box. It can't see that there's this delicious apple just outside of its field of view. But when this influencer agent chooses to move towards that apple, which it only ever does when there are apples present, that signals to this other agent that there must be food that it can't see, allowing the influencer to gain influence. And we see a similar moment here. This agent has been cleaning the river, and it can't see whether any apples have appeared. But when the influencer chooses to stay still, that signals that no apples have appeared, again allowing it to gain influence. So what we're seeing is that the influencer agent has basically learned to communicate about the presence of food in the environment via its actions, which signals information to other agents and allows it to gain influence. So you can think of it like a little bee waggle dance. But we think this is really encouraging. So the next experiment we did was to train an explicit communication protocol via the influence reward. So what we're doing here is the agents are getting an additional policy head that's going to decide which of a set of discrete symbols to emit and place on this cheap talk communication channel for every other agent to observe in the next time step. And it's a cheap talk channel because agents are free to ignore what's placed on it. And the idea here is that we're going to train this communication policy using the influence reward. And we think this is really interesting because we actually think this overcomes the problem that I mentioned earlier, that influence is not necessarily beneficial to the listener. We think that influential communication should benefit the listener, and here's why. The agents are free to ignore what's placed on the communication channel, and we're looking at the influence on their action policy they're actually using to collect environmental rewards. So this policy is trained with the environmental reward. So the only reason that an agent is going to change its action, a self-interested greedy agent is going to change its action as a result of a symbol on the channel, is if that's going to help it obtain its own environmental reward. So we have this hypothesis that influential communication should benefit the listener. Now, I should just point out that previous work on emergent communication in Marl has shown that for self-interested agents, cheap talk just doesn't work. So we can say theoretically that as agents' interests diverge, the amount of information that gets placed on the channel goes to zero. And empirically, we've seen that when agents are cooperative, they might learn to communicate, but when they're self-interested, this really doesn't happen. But we see that when we train the agents with this influence reward, the communication protocols are actually more meaningful in the sense that they're communicating more consistently about what they're doing in the environment. And we also see higher mutual information in moments of high influence, although we do see that the influence is quite sparse. So this is really encouraging. And we see that agents that are trained with the influence reward to communicate achieve more collective reward. So again, evidence that they're cooperating better in these environments. But this is my favorite finding. So what you're seeing here is the amount of influence from an influencer agent on the y-axis on an agent that's being influenced, the influencee, on the x-axis. And what you can see, and what we found from sampling hundreds of trajectories from the environment from different hyperparameter settings, is a really consistent effect where agents that are more easily influenced, agents that are essentially better listeners, if you will, actually tend to get higher individual reward. So we think that this is evidence that it validates our hypothesis that some useful information is being placed on this channel that's helping agents to obtain their own environmental reward. And I just want to tie back to some readings in social psychology on human communication. Actually, Tomasello proposed that humans, like young children, learn to communicate as a way to influence their conversational partner. And actually that this ability to influence the partner via communication has been interpreted as evidence of a capacity to form shared goals with others, which helps humans learn to cooperate in a wide range of activities. So we think that this idea of influence through communication could be a really promising future direction in emergent communication work. So I just want to throw this slide in to make Joelle Pineau happy if she's here. So we show that if we actually test these influence models across 5 different hyperparameter settings with 5 random seeds each, we see consistent effects of it doing better, so that's nice. I also want to throw in some caveats. So as I mentioned, whether the action-action influence is pro-social is going to depend on the specifics of the environment. We think that because our agents were trained with both the influence reward and the environmental reward, learning to communicate may have been the cheapest way to gain influence while still obtaining their own reward. We think that the influence through communication removes this drawback in the sense that influential communication should benefit the listener, but this depends on the agents interacting repeatedly. So if in some future work where agents had an agreed upon protocol that they could use to interact with a new agent that they'd never seen before or were never going to interact with again, then the agent could potentially put false information on the channel, it could lie, and still gain influence from that. But, of course, if it did that with an agent that it's interacting with repeatedly, that agent would begin to ignore it, and it would lose influence over time. So that's why they don't learn to do that in this setting. So, in conclusion, we think that social influence is a unified method for promoting both coordination and communication in multi-agent settings. And unlike prior work, it allows agents to learn socially from each other without requiring a centralized controller and without having agents view each other's rewards. So we think this is a bit of a more realistic approach to social learning in Marl. So thank you very much, and I'm happy to take questions.
Yeah, please come up to the microphone.
Hi, beautiful talk. I have a question. In the case you have multiple influencer agents, how would you go into disentangling the fact of their independent actions over the other agents, given that now not only the past mutual information are important, but also the future mutual information of the action of the other agents are important because they're strategic.
Right, so that's exactly what we get from doing this counterfactual. So when we run the counterfactual, we keep everything about the situation the same. So we've saved the state of the environment at that time step, we've saved all the other agents' actions, those go into the model exactly the same as they were. The only thing we tweak is the agent's own action. And so any difference that we see in the predictions from tweaking that action is exactly the causal effect of that action alone. Thank you.
It was a really fascinating talk. Thank you. I'm just wondering if you have made any attempt to inspect what meaning was in the symbols that were being communicated to kind of uncover what they were saying.
Yeah, we actually did look into that, and that was thanks to Angeliki, who's sitting right over there. She did some great work in this. But we found that the agents actually tend to learn to communicate about what they're doing in the environment. So perhaps that's the easiest way to stumble upon a communication protocol, sort of just say what you're doing, say if you're going after an apple. So we see a high correlation there. Yeah.
Right.
Yeah,
Great talk. There are a bunch of work on graph structure of social interactions and how the number of in degrees and out degrees can change information gain depending on the task at hand. So would it be fair to say that in the case of your good listeners that you were mentioning, if one sort of plotted out the graph or constructed the graph of the interaction, they just have more in degree? And so there is a particular betweenness or other kind of score, maybe eigencentrality or some other thing that could sort of, without running the agents per se, tell us in which problem, what's the optimal level of being influenced or influencing?
Thank you. That's a really interesting question, and it would be nice to take some graph measures and apply them. I would argue that whether a node is connected in the graph here is actually whether they have the ability to communicate. So we actually think of this as like a fully densely connected graph where every agent is connected to every other agent in the sense that they can place symbols and the other agents can observe them. But what we find is that the amount of agents that actually learn to communicate is quite sparse. So weirdly, only certain pairs of agents actually tend to learn to communicate. I think that's because it's very difficult to stumble upon an effective emergent communication protocol from just randomly emitting symbols. So that might be why it ends up being sparse, even though it starts out fully connected.
So the evolution of that graph would be super interesting.
Yeah, definitely. Thanks.
All right, let's thank our speaker again, and congratulations again on the award. Right. Our first spotlight talk of the session is called Maximum Entropy Regularized Multi-Goal Reinforcement Learning and will be presented by Rui Zhao.
Thank you for the intro. Hello, everyone. I'm Ray. Today, I give a presentation about our recent work, Maximal Entropy Regularized Multi-Goal Reinforcement Learning. The work was done at Siemens and the Ludwig-Maximilian University of Munich with my collaborator Xudong Sun and my professor Volker Tresp. So in multi-goal reinforcement learning, the agent learns to achieve multiple goals with a goal conditional policy. During learning, the agent first collects the trajectories into the replay buffer, and later those trajectories are selected randomly for replay. However, we observe that the achieved goals in the replay buffer are often biased towards the behavior policies. From a Bayesian perspective, when there is no prior knowledge about the target goal distribution, the agent should learn uniformly from a diverse set of goals. So we want to encourage the agent to achieve a diverse set of goals while maximizing the expected return. To do this, first, we propose a novel multi-goal reinforcement learning objective based on weighted entropy, which is essentially a reward-weighted entropy objective. And secondly, we derive a safe surrogate objective that is a lower bound of the original objective to achieve stable optimization. Thirdly, we developed a maximal entropy-based prioritization framework to optimize the derived surrogate objective. In the end, we evaluate the proposed method in the OpenAI Gym robotic simulations. The weighted entropy was proposed in 1971. It is an extension of Shannon entropy. The definition of weighted entropy is shown here, where omega is the weight of the event and p is the probability of the event. We substitute the weight with the reward and propose the reward-weighted entropy. This objective encourages the agent to maximize the expected return as well as to achieve more diverse goals. In this equation, we use tau g to represent all the achieved goals in the trajectory. However, this objective is unbounded. We propose a safe surrogate objective, which is proven to be a lower bound of the original objective. To optimize the derived surrogate objective, we developed this maximal entropy-based prioritization framework. So first, the agent collects the trajectories into the replay buffer. And at each epoch, we use a latent variable model to estimate the underlying goal distribution in the replay buffer. And based on this distribution P, we construct a proposal distribution which is proportional to 1 minus p multiplied by p. And we prove that this new distribution has a higher entropy than the original distribution. Afterwards, we sample the trajectories directly from the new distribution and update the policy using DDPG and high-side experience replay. To compare the performance, we compare baseline methods, including deep deterministic policy gradient, and the combination with prioritized experience replay, and also the combination with high-side experience replay. So the experimental results is shown here. We test our method in 6 different environments, and our method achieved the best performance. And for the training time, our method is a little bit slower than the simple baselines, DDPG and HER, but it's still much faster than prioritized experience replay. To verify the consistency between the developed framework and the stated theory, we calculate the entropy of achieved goals during training. From all these 3 figures, we can see that the entropy of the goal distribution is indeed increased during training. To summarize, our approach improved the performance by 9 percentage points and the sample efficiency by a factor of 2, while keeping computational time under control. The take-home message is that training the agent with many different kinds of goals, always a higher entropy goal distribution, helps the agent to learn. Our code is available online, so welcome to modify our code and extend the idea. Our poster number is 32, so see you at the poster. Thank you.
Right, our next talk is called Imitating Latent Policies from Observation, and will be presented by Ashley Edwards.
All right, thank you for the introduction. Thank you for everyone for coming to my talk. I'm going to be talking about imitating latent policies from observation, and this is joint work with Himanshu Sani, Yannick Stroker, and Charles Isbell. So imitation learning is an approach for training agents to learn behaviors from expert observations and actions. So typically you need actions in order to train these agents, but more recently people have been interested in training agents just from straight state trajectories. So this is useful if you're interested in learning from things like videos. So some kinds of approaches for this are to learn reward functions for training agents with reinforcement learning, or you can learn dynamics models to infer the types of actions that were taken between states. The problem with both of these approaches is that it usually requires a lot of interactions with the environment in order to learn. But if you think about how humans learn, we usually don't have to actually really figure out how to do the task after we watch somebody do it. We can just sort of do it instantly. For example, if you think about when we're learning how to play a video game, we can just watch our friend play it, and then once we take the controller, we just need to sort of figure out what the controls are in order to be able to play the game. So that's sort of the motivation for how our approach is going to work. So first we're going to learn something called a latent policy just from the observations, and then we're going to learn how to act just by taking a few steps in the environment. So in our approach, we're given a sequence of expert observations, and so we define a latent action as the sort of reason why that transition occurred in our trajectory. For example, this latent action might be something like a real action, like moving to the right, or it might be something like bumping into a wall, which isn't an actual action that we have in our action set. And so we define a latent policy as the probability of taking a latent action in one of our states. And so again, in our approach, we're going to try to learn a latent policy given a sequence of observations, and then we're going to take a few steps in our environment to align our latent actions with the real actions that we can take in our environment. So how do we learn this latent policy? So we introduced something called a latent policy network, which given a state, learns to predict each of the next states that we can have given our latent action. So the way that we train this is we have a generative model that finds the predicted next state that is closest to an observed next state. And so what we do is we we move the closest states closer to the actual state. What this does is it allows us to learn all the different modes of the types of transitions that we can see. And then we're going to simultaneously learn something called a latent policy, which is it tells us the likelihood of our expert taking one of our latent actions in a particular state. And the way that we train this is basically we say, okay, we're going to take the expectation over all of our predicted next states, given that latent policy, and then we're going to just minimize the distance between that and the observed next state that we have. Once we learn our latent policy, we need to align the latent actions with the real actions that we can observe in our environment. So we're just going to take a few steps in the environment to learn this alignment. So what we're going to do is we're going to have the agent interact with the environment, get a transition like state action next states. We're going to find the prediction that looks the most like this transition that we've observed, and we're just going to train it using like a supervised learning or supervised loss on the action label. So we tried this out in a few different environments. So as a reminder, we don't actually have any access to expert actions, and we don't have access to the reward function. We're only going to use that for evaluation. And we compare that to behavioral cloning from observation. And so we try this in classic control problems, and we see that we're able to more quickly achieve high reward compared to the environment interactions than behavioral cloning from observation. We also try this out in visual domain, so this is coin run, and so we are also able to achieve higher reward than behavioral cloning from observation. So that's it. So if you're interested in finding out more, come to our poster number 33, and thank you everybody for your attention.
Great. Our next talk is called Solar, Deep Structured Representations for Model-Based Reinforcement Learning. Will be presented by Marvin Zheng.
Okay, thank you. This is joint work with Shared Vikram, who had equal contribution, Laura Smith, Peter Abil, Matt Johnson, and Sergey Levin. The goal of this work is to be able to do efficient reinforcement learning from images. Data efficiency is important in settings where data collection can be expensive and dangerous, such as this robot arm learning manipulation tasks directly from its camera feed. Deep reinforcement learning has worked well as a general-purpose framework for learning from complex observations such as images. But most deep reinforcement learning success stories come from model-free methods, which are known to be not data efficient. For example, soft actor critic is one of the most efficient model-free methods, and it requires 4 hours to solve the image-based valve turning task on the left. The block stacking task on the right requires 2 hours to learn, but this task is solved from the much lower dimensional state of the robot, not images. To minimize human and robot costs, we would like to learn robotic tasks like these from images in an hour or less. The common answer for efficiency in reinforcement learning is to use model-based methods. However, the model-based methods that have worked for image-based tasks have typically relied on accurate forward prediction for planning, and this amounts to video prediction, which is itself a difficult problem. The main idea in this work is that if we can learn a state representation from images that enables simple modeling, then we can use a model-based method that does not rely on accurate prediction, thus enabling greater efficiency. Note, however, that the latent state representation itself does not have to obey simple dynamics, as I'll explain. The model-based reinforcement learning method we use is known as LQR-FLM, which is shown here has been successfully applied to a variety of robotic learning settings. One of the key ideas in LQR-FLM is to fit what we refer to as local models, which are simple models that are fit to data from the current policy. The local models are then used for a policy improvement step, which in this case is LQR dynamic programming. When given access to a compact, low-dimensional state representation, such as joint angles or positions of objects provided by motion capture, local models can work well even for complex dynamical systems such as robots because they only need to accurately model a local region around the current data. This leads to data efficiency because local models are simple and do not need to see enough data to be accurate forward predictors. Specifically, LQR-FLM parameterizes the local models as linear Gaussian and quadratic for the dynamics and costs respectively. Though this method can work well even for complex dynamical systems with a simple state representation, the limitation is that linear dynamics and quadratic cost models are too limited to even locally model complex states such as images from a camera feed. This motivates our work, in which we accomplish efficient reinforcement learning from images by combining local model-based reinforcement learning with structured representation learning. Essentially, we decompose the system into first a latent state representation that can be accurately modeled by stochastic linear dynamics and quadratic cost. Second, we assume that this latent state generates the image observations that we see through a complex observation model F that we represent as a deep convolutional neural network with parameters gamma. This model is similar to the structured variational autoencoder from prior work, and as detailed in the paper, we use the same amortized variational inference approach to learn the model. Through this decomposition, we are able to automatically discover a state representation that enables LQR-FLM to successfully and efficiently learn policies for complex image-based tasks. We name our method SOLAR, which stands for Stochastic Optimal Control with Latent Representations, and we find that SOLAR is more efficient than prior model-free and model-based methods on a range of simulated and real-world tasks. Here we'll focus on the real-world results. In this block stacking domain, we test multiple initial positions of the robot arm, and we find that we can transfer a single representation to solve all of the positions, further increasing the efficiency of our method. We can see that for this particular initial position, SOLAR learns good performance in about half an hour, and all initial positions take between 30 minutes to an hour. Our method is also the only tested method that solves the hardest initial position where the block starts on the table, and this is an advantage of not requiring accurate prediction into the future, which can hinder performance for harder tasks. On the task of pushing a mug onto a coaster, we learn with similar efficiency, despite the fact that we add an additional challenge where we only provide the learner with sparse rewards. This is done by having a human press a key only when the robot fully succeeds at the task. And for more details on how we incorporate this into our method and solve this challenge, please come see poster 34 tonight and check out these other resources. Thanks very much.
Great. Our next spotlight is called Dimension-Wise Importance Sampling Weight Clipping for Sample-Efficient Reinforcement Learning, and will be presented by Seung-Gul Han.
Thank you for the introduction. My name is Seung-Gul Han, and I'm from KAIST. My presentation title is Dimension-Wise Importance Sampling Weight Clipping for Sample-Efficient Reinforcement Learning. I first briefly explain about our contributions. One of popular RL algorithm, proximal policy optimization, is a stable on-policy RL algorithm, but it has two limitations. PPO has vanishing gradient problem in high-dimensional tasks, and on-policy learning of PPO is sample inefficient. To overcome these drawbacks, we propose dimension-wise importance sampling weight clipping to solve the vanishing gradient problem, and a proposed generalization to reuse all the samples. PPO updates the policy parameter theta to maximize importance weighted advantage as equation 1. PPO updates theta when the IS weight is not clipped, and otherwise it does not update theta. This clipped IS weight enables stable policy update of PPO. However, the gradient of clipped sample becomes 0 and it reduces sample efficiency. We call it the vanishing gradient problem, and larger IS weight makes more zero gradient samples. For higher dimensional tasks, IS weight is much larger than lower dimensional tasks. The figure shows that the average IS weight of humanoid, which is much larger than PPO clipping vector, and the amount of gradient vanishing is about 70%. To overcome this problem, we propose two things. One is clipping dimension-wise IS weight instead of total IS weight of PPO, and the other is adding IS weight loss, which enables stable learning. Then this updates theta to maximize dimension-wise importance weighted advantage as equation 2. Then even if dimension-wise IS weight is clipped for some dimensions, this has other dimensions that are not clipped. So the policy is updated to the gradient of unclipped dimensions. Hence, the sample gradient of disk does not vanish in most samples. Also, we want to reuse the previous batches to enhance sample efficiency. Disk reuses all the batches that satisfies IS condition to avoid too much clipping. This method is proposed by our previous work, Amber. In addition, ICE calibration to estimate the advantage of the old samples is needed, so we combine GAE and retrace of Impala to calibrate IS. As a result, this reuses a large number of sample batches for training. Finally, we evaluate our method on Mujoko tasks in OpenAI Gym and compare the performance with PPO baselines. The figure shows that DISC, the orange curve, significantly enhances the convergence performance in various high-dimensional tasks, such as ant, humanoid, and humanoid stand-up. We also compared our method with other state-of-the-art RL algorithm, and the table represents max average return of DISC and other RL algorithm. It shows that DISC has top-level performance in 5 tasks out of the 6 considered tasks, and especially for humanoid stand-up, DISC has much higher performance than other algorithms. In conclusion, DISC extends PPO by dimension-wise ICE clipping and polygeneralization, and it solves the vanishing gradient problem and enhances sample efficiency. Finally, DISC achieves top-level performance as compared to other state-of-the-art RL algorithms. Thank you for your attention, and the location of poster session is number 35. Thank you.
Great. So next we have our second long talk of the session that will be called Structured Agents for Physical Construction and presented by Jess Hamrick.
Me too.
Yeah. Maybe this will work.
Can we that? Thanks. Just move this over to the other screen, sorry. What? Yeah, I just can't see my mouse pointer. One second. Okay. Sorry about that. All right. Hi, my name is Jess Hamrick, and I'm interested in building agents that build things. Humans are a construction species. We build things everywhere and out of everything. Children are driven to stack blocks. We build shelter out of parts of the environment around us. And we build space stations in the sky. And we don't just stop with the physical world either. We also construct things in the more abstract sense of the word. For example, we construct scientific theories out of pieces of knowledge and hypotheses. In this project, we were interested specifically in the topic of physical construction, which is the ability to compose objects subject to physical dynamics in order to serve a function. This ability is crucial for agents to have if we want them to be able to flexibly act and creatively create new things out of parts of the world around them. To this end, we developed a suite of challenging physical construction tasks for our agents to solve. And in order to solve them, we developed a new type of structured agent that uses structured representations, object-centric relative actions, and a combination of both model-free and model-based methods. So let me first describe the construction task that we developed. In these tasks, the agent sees a scene that looks like this, with a set of blue blocks below the floor and some number of red obstacles above the floor. The agent's job, is it flickering?
Yes.
Oh. Let me try unplugging it and plugging it back in.
Here, I'll put this right towards you so you can see what's on the screen.
Is it still? Okay, maybe it's, oh. It's working before.
What's your refresh rate?
Not sure.
Can you do it mirrored or
Yeah, I can do it mirrored. Sorry about this.
Let's see what, you got a Mac or is it, or no, it's not. Let's see if that does anything.
I think it's the connector, probably.
Yeah, it might be.
All right, I'm gonna
Let's try this one.
continue trying to talk while we fix this. Okay, so these are our construction tasks. So again, there's the blue objects below the floor and the red objects above the floor, as I was just showing you before. And hopefully, as we'll see in the screen in just a moment, the goal of the agent is to pick up the blue blocks that are below the floor and place them into the scene while avoiding the red obstacles. The agent can also choose to make the blocks sticky, in which case the blocks will stick to any other object that they come into contact with. So we developed several different objectives within this type of environment for our agent to solve. In the first task, called the silhouette task, the goal of the agent is to stack the blocks to match these green silhouette targets. Here's an example solution to the silhouette task, where you can see some of the blocks that the agent has made sticky. They're the ones that are teal colored, and the little gray dots between the blocks are showing where they're actually sticking together. In this particular task, the agent gets a reward of 1 for each target that it fills in, and a reward of minus 0.5 per block that it turns sticky. In the connecting task, the agent's job is to stack the blocks from the floor to connect them to these targets in the sky. This task is a bit more difficult now because the agent has to actually design a solution to the task as opposed to just copying a solution that it's been given. Finally, in the covering task, the goal is for the agent to stack blocks to cover these obstacles from above. You can think of this in terms of building shelter from the rain. If it rains from above, then the obstacles that are covered should stay dry. So how should an agent actually interact with these types of environments? Well, the sort of standard choice of action, which other projects looking at similar types of environments have used, would be to take absolute actions. So for example, place block D at position 7.2, 8.5. But if you think about it, if I were to talk to you about this sort of environment, say if I were instructing you how to solve this task, I would never tell you place the block at position 7.2, 8.5. I would say something more along the lines of place block D on the top left of block B. So we can get agents to do this perhaps by having them directly select the object they want to pick up, the object they want to place it on top of, and then an offset location that says where to place the object relative. You can think of this in terms of, say, like stacking Lego bricks. To do this, you would pick up a Lego, put it on top of another Lego, and you would have to choose the particular dimple that you want to place it on for the position. However, there's a bit of a problem here, which is that standard RL architectures assume a fixed size action space. But if we're defining our action space in terms of the number of objects in the scene, then we have different numbers of actions depending on how many objects there are. And as the agent adds more objects into the scene, the action space will grow. So to deal with this issue, we developed a new type of agent that we call the GNDQN agent for graph networks. This agent is going to operate over the scene as a graph, which, as we'll see, will be important for actually dealing with this variable size action space. So here we have the scene. What we're going to do is encode this as a graph. So each object in the scene corresponds to a node in the graph, where the nodes have properties corresponding to, say, the object's position, its size, its type, so on and so forth. So now we need a network that can actually process this type of representation. And for that, we're going to use something called a graph neural network. Now, graph neural networks have been around for quite a while now, first pioneered by people such as Gori, Scarcelli, and many others. And last year, my colleagues and I released a review of some of this literature and created a unified architecture that we called graph networks, and that you can see in this diagram on the right here. Now, I don't have time to go into all of the details of how graph networks work, but if you're curious, you can check out this reference. I'm just going to make 3 points about how they work that are sort of relevant for this talk. So the first thing is that graph networks take in graphs as input, and they return graphs as output. So as opposed to, say, like a convolutional neural network, which takes in a tensor as input and gives you a tensor as output, a graph network takes in a graph, which is a collection of nodes and edges. The second point is that it doesn't matter what order you give those nodes and edges to. The graph network is invariant to that permutation. So this is in contrast to, say, an RNN, which can process a set of things but has to do so in a particular order. Graph networks, it doesn't matter what the order is. It'll always give you the same answer. And then finally, graph networks can scale to different numbers of nodes and edges. So unlike, say, an MLP, which has a fixed size input and output, a graph network can scale to any size graph. It might give you different answers for different size graphs, but it can always handle a different size graph. So you can see now how particularly this last property, is useful for our variable size action space in the context of these construction tasks. So here we have our graph that represents all the objects in the scene. Doesn't matter how big it is. We pass it to our graph network. It gives us a new graph with activations on the edges of this graph. And we're going to take these activations to be Q values and treat them as actions. So in particular, if, say, we wanted to pick the best action for the agent to take, that would correspond to whichever edge that action is on, tells us which objects we're going to manipulate. So in this case, the best action is maybe on the edge between block D and block B, so that would tell us pick up block D and place it on top of block B, and then the particular index of that action is going to tell us the precise location relative to those two objects. So in this case, this might be place block D on top of block B on its top left. Again, if this is a bit confusing, just remember the Lego analogy. This particular location of the Q value is sort of specifying like which dimple to place the Lego on. And I just want to emphasize here that even though we sort of have a different action space here, it doesn't necessarily make the problem simpler. With a scene of only 10 objects in it, according to the way we've defined this action space, we would have over 1,000 actions. So we have a huge action branching factor here. It doesn't necessarily make the problem simpler. We compared this graph network agent to a bunch of other types of architectures, including a different type of graph network agent that uses a continuous variant of these relative actions, RNNs, CNNs, a bunch of things. I don't have time to go into the details of all of these comparisons and all of these architectures, but come by our poster if you're curious about the details. So in examining this graph network architecture, we had three key questions that we were interested in answering. First of all, what's the contribution of these relative actions as opposed to absolute actions? How important is it that it's actually placing the objects relative to one another? Secondly, what is the contribution of the structured representation of the graph? Does it matter that we have encoded the scene as a graph and that are processing it with a graph network? Or could we get by with some more standard methods like RNNs and CNNs? And then finally, if we think about human construction, we don't just reactively build things. We plan what we're going to build. So planning is a really important component of human construction, and so one thing that we were curious about too was whether planning might also make a difference in the context of these construction tasks for our agents. So looking at the contribution of relative versus absolute actions, what I'm going to show you is a comparison between the very best agent that we trained using absolute actions and our relative GNDQN agent. On the top row of plots, what I'll show you is the reward averaged across all levels of difficulty in our task. So for each of our tasks, we define several levels of difficulty that we use to train our agents. So that'll be averaged across those levels of difficulty. What you can see is that in all of these cases, the GNDQN agent is strongly outperforming the best absolute agent. And these differences become even more prominent if you look at them only on the hardest level of difficulty, where in some cases the GNDQN agent is outperforming the absolute agent by twice as much reward. In the case of structured representations, we can perform a similar type of comparison where we can take a look at the best unstructured agent, like an RNN or a CNN, and compare it again to this GNDQN. And as I mentioned, we had a continuous variant of these relative actions, so all of the agents that I'll be showing you here actually are taking a type of relative actions. The thing that's different between them is the type of structure in their policy. So again, we see across all difficulty levels, the GNDQN agent is outperforming the unstructured agent, and this is even more dramatic at the hardest levels of difficulty. These differences are, clear from looking at the bars, but it's sort of even more striking if you take a look at them qualitatively in the videos. So here on the left, you can see the best agent taking absolute actions on the silhouette task, and on the right is our GNDQN agent. You can see that the best absolute agent really kind of struggles to solve the task. It doesn't place the objects quite where they're supposed to go. Sometimes it tries to place objects inside each other or collides them with the obstacles. It doesn't always quite make appropriate use of sticky blocks. And in general, just doesn't make very intelligent decisions in every case about how to act. The GNDQN agent, on the other hand, does make good decisions about all of these things and is able to solve the task on most of the scenes. In the connecting task, where again the goal was to stack the blocks to connect the floor to these target locations, we see a similar pattern of behavior. The best absolute agent has learned this sort of degenerate strategy of just stacking up the blocks on the side of the screen, and it sometimes stacks them over to the side in order to try to reach to the targets, but it's never able to actually stack them in between the obstacles to reach the targets in the middle. In contrast, the GNDQN agent is able to stack blocks to weave in and out of these obstacles and ultimately solve the task on the majority of the scenes. And you'll notice that these tasks are not easy. I mean, the performance of our agent maybe makes them look easy in some cases, but these obstacles are sometimes very close together, and it's very hard to exactly place the objects where they need to be. And yet, the GNDQN agent is able to do this in a lot of cases. Finally, in the covering task, where again the goal is to cover the obstacles from above, we see a similar strategy by the absolute agent, where it's stacking the blocks up on the side of the screen and trying to curve them inwards to cover them from above. This sometimes works okay in narrower scenes like this one, but in wider scenes it doesn't really work that well, and often the blocks will actually fall over and collide with obstacles. The GNDQN agent, on the other hand, has learned this more sophisticated strategy of building these umbrella or T structures in order to solve the task. And it's able to actually flexibly compose them into even bigger, more interesting structures like arches. Okay. So coming to our last question, what is the contribution of planning? So as I mentioned, planning is an important component of human construction, and in a lot of cases, that's because we actually don't have, an infinite number of resources that we can use. So, if you consider like real construction problems, we might only have access to a limited amount of building supplies that we can use. However, in contrast, the agents that I've been showing you before have all been allowed to use an infinite number of blocks to solve these scenes. So to deal with this, we designed a new type of task that would sort of get at this question of planning with limited resources, and we called this the covering hard task. So the objective is actually the same in the regular covering task, but the difference here is that the agent only has the initial 7 blocks that it's allowed to use, so it can't use any more than that. And we also packed the obstacles a little bit more close together to make the task even more difficult to solve. To augment our GNDQN agent with the ability to plan, we used this learned queue function using queue learning as a prior for MCTS. And we can choose to do this either at training time or testing time. So at test time, we just take the pre-trained queue function, use it as a prior for MCTS. During training time, we actually have the agent run MCTS during training, and then we take the actions resulting from MCTS and add them to the replay buffer and continue to do queue learning as normal. So here I'm going to show you the results comparing the model-free GNDQN agent and then the two variants using planning both only at test time or both at training and test time. And we can see on the x-axis here the contribution of varying the test budget. And the thing I want you to pay attention to is that we can get very good performance here even with very low test budgets. So here we're seeing about a 30% improvement in reward in comparison to the model-free agent, even using just 10 steps of planning. And the other tasks, some of them like silhouette, the model-free agent is already basically at ceiling level performance, so we don't really see any improvement there. But in others, like in the connecting task, we similarly see an improvement when we add planning to the mix. Again, just a qualitative demonstration of what this looks like. We'll see that the difference between the model-free GNDQN agent and the model-based GNDQN agent is that the model-based agent has learned how to use sticky blocks more effectively. So even though sticky blocks come at a price, by using them, it's able to cover much more of the obstacles than it otherwise would. So here again, you can see the model-free agent didn't use any sticky blocks because it's learned to be a little bit afraid of using them because they cost something. But the model-based agent is able to plan around this and achieve a better solution. A final set of results I just want to show you are in terms of generalization. So for example, in the silhouette task, during training, we always trained our agents only on scenes of up to 8 target silhouettes. But we can test it on scenes of even larger numbers of blocks, for example, up to 9 target silhouettes or even 16 target silhouettes. And we see that it's able to generalize very well in these cases, in contrast to, say, the RNN agent, which isn't really able to generalize at all. The reward here actually goes up because there's more targets to match, and this is what we would expect from an agent who's actually learned what the task is, which is to fill in these target silhouettes. Here you can see a qualitative demonstration of the agent actually solving this 16-block silhouette task. We see similar results in the connecting task as well, where we varied at test time the locations of these targets at the top of the screen. And again, we find very strong generalization performance, particularly in our model-based agents. Okay, so just coming back to these questions that I asked at the beginning of the talk, I asked, what was the contribution of relative actions, structured representations, and of planning? And the answer in all three of these cases is that they're all really important. Relative actions bias, 80 to 130% improvement in reward over absolute actions. Structured representations bias, 25 to 155% improvement in reward over unstructured representations. And planning gives us almost a 30% improvement in reward in covering hard. So just to wrap up, in this talk, I introduced a suite of challenging construction tasks and tested a bunch of existing RL algorithms on these, finding that sort of standard methods that take absolute actions that use unstructured representations really struggle to do well on these tasks. We developed a new type of structured agent that uses a combination of structured representations, object-centric relative actions, and a combination of both model-free and model-based components that is able to solve these types of tasks. Of course, this is really only the beginning. We want to explore agents that are able to construct many more types of things, looking at bigger scenes, harder tasks, more interesting types of physics, connecting up with perception and continuous control, learning environment models, and much more. So if any of this is interesting to you, please come by our poster tonight at Pacific Ballroom number 36, and we'd be happy to talk to you further. Thank you.
We have time for a couple of questions. Please come up to the microphones.
Hi. So thanks for the very nice talk. So recurrent neural networks, in your case, were performing worse than the graphical networks.
Yes.
Can you tell whether it is related to the trainability of recurrent neural networks in our current state of the technology, the art, or it is a fundamental, or it is more fundamental? Because naively, one would imagine that the human being is, or human brain is working more like a dynamical system than as a graphical neural network. So is it fundamental, or it's just?
Yeah, good question. So I think this is a bit of a fundamental problem in this particular case, because to process this scene with a recurrent neural network, you have to pick an ordering that you process the objects. So you have to say, which object you want to feed into the neural network first. And there isn't like a strict ordering in these types of scenes. So that's always going to be a limitation of recurrent neural networks, is that they can't process the whole scene sort of in parallel and at once. Whereas with graph neural networks, you can do that. Thanks.
All right, let's thank our speaker again.
Thanks. Thank you.
All right, our next spotlight is called Learning Novel Policies for Tasks, presented by Yunbo Zhang.
Thank you for the introduction. My name is Yunbo Zhang from Georgia Tech. Today, I will be presenting our work, Learning Novel Policies for Tasks. This is work jointly done with Wenhao Yu, my colleague, and my advisor, Greg Turk. So in deep reinforcement learning settings, oftentimes we want more than one solution to a problem. Consider a forward locomotion task. Maybe we want different locomotion styles for a leg robot. Here in the figure, we can see that even for a two-dimensional hopper, there might be different styles for it. However, in a principal way, finding a collection of novel policies is difficult. Here we propose an approach that we can find a collection of policies where all of them can solve the task in using different styles. There are two key aspects of our method. The first one is the novelty measurement function. We want to define the function that measures the novelty for trajectory compared with all other trajectories from all other policies. The second aspect is a policy gradient update. We want to make sure that our final policy gradient is a good compromise between task and novelty objectives. And this leads to our main contribution, task novelty bisector, or TNB. Here is a high-level overview of our method. We first define a separate reward function for novelty that is apart from the task reward. We train a policy using task novelty bisector to balance the optimization of task and novelty. We then update the novelty measurement function and repeat this entire process until we have enough number of policies. To measure novelty, we simply use the reconstruction error of a fully connected autoencoder taking input as a state sequence. For every policy trained, we train a corresponding autoencoder to capture the feature of that policy. For a set of autoencoders, we just define the novelty reward function in this form. Now we have the task reward and the novelty reward. We want to find a good combination of the two. A common way of doing this is to use weighted sum of the two terms. However, finding a good weight for the two terms is very difficult and requires a lot of tuning. Here we propose an alternative solution. We compute the policy gradient for the task reward and novelty reward individually. And then we decide the final policy gradient using the following rules. If the two gradients are pointing in the same direction, we pick the angular bisector of the two gradients. But if the two gradients are pointing in a different direction, we just project the task gradient to the perpendicular plane of the novelty gradient. This design makes sure that the task objective will always be improved, and the novelty objective will never be harmed. Here we did some experiments with a reacher. If we train this reacher with PPO, a PPO-trained policy will always give us a trajectory look like this. By feeding this policy into our loop for several times, we're able to get several different policies where we can see all of them complete a task, but with different styles. We find that our method could be further extended to solve tasks with deceptive reward signals. Here we design a deceptive reacher task, where initially place a reacher inside of a solid pocket, and the only reward signal is the distance between the end effector to the target. If we train this environment in PPO, this trajectory is usually what we get. By feeding this trajectory and the policy into our method, we're able to get several more policies. Here we can see 4 of them, and 3 of them actually solve the problem, and they all perform in different styles. Thank you so much. If you would like to see more details, please come to my poster session at number 37.
Right, the next spotlight is called Taming Mammal, Efficient Unbiased Meta-Reinforcement Learning, presented by Hao Liu.
Good afternoon. I'm very excited to present my joint work with Richard Search and Tsai Yun during my internship at Salesforce. It's called Taming Mammal. We consider a widely used algorithm in meta-reinforcement learning called a model-agnostic meta-learning, MAML. The goal of MAML is to learn a good initialization across the distribution of tasks. aiming to generalize to new tasks with a few samples by gradient descent adaptations. However, it is highly non-trivial to accurately estimate the gradient in MAMO. Because by chain rule, we can say that the gradient of MAMO involves a highly sophisticated Hessian, as shown in the slides. And it is not very easily computable through current auto-differentiation system. As you can see, if you apply like a TensorFlow gradient twice, you will only get the first green term, and the red term is actually missing. So current estimation methods gives you a biased estimate, and our goal is to get unbiased and hopefully low variance estimate. So our goal is to get computational efficient solution. We propose a surrogate function called TMAMO. The basic idea is hopefully we can get an unbiased estimate through auto-differentiation, and we can incorporate the contravariance into the Hessian to reduce the variance of the full Hessian estimate. The TMAMO consists of a sum of weighted reward and weighted contravariance. And you can see in the forward pass, TMAMO gives you an unbiased estimate. And in the backward pass, the twice order derivatives give you the exact Hessian estimate. And more nicely, in the paper, you can see that we prove the contravariance actually can reduce the variance into the Hessian. And so you may ask, how do we get the contravariance? We can learn the contravariance for each task, like the widely used data value function baseline, or we can also learn meta contravariance by MAMO itself. Although you will get the non-optimal contravariance, since in the sense that MAMO is still biased, but we can prove that TMAMO also gives you unbiased solution, and this would be very scalable since it's independent of the number of tasks you are curious about. So here is the summary list of comparison with baselines. We see the original MAMO, and we see a bunch of other recent work, including DICE and OS3. And we see that TMAMO has a very nice property in that it is both unbiased and low variance. And so we firstly evaluate the variance and the corresponding mean reward. And we see that TMAMO reduces the variance and also improves the mean reward performance. And we also did a through benchmark comparison. And we see that TMAMO, both versions of TMAMO actually get a higher sample efficiency and final convergence performance in most of the meta-IO tasks. And finally, thanks for your attention, and welcome to our poster. Thank you.
The next spotlight is called Self-Supervised Exploration via Disagreement, and will be presented by Deepak Pathak.
Hi, everyone. I'm Deepak Pathak. This is joint work with Dheeraj Gandhi and Abhinav Gupta at CMU. So exploration has been a major challenge over the last few decades in sensory learning. There has been a number of approaches which have been proposed in the literature. Notably, there are a number of recent works which are able to explore even without requiring any extrinsic reward at all. However, most of these approaches are still sample inefficient and takes millions of samples in simulation. This thing is fine for simulation, but very hard to scale to real robotic setups. Moreover, many exploration methods which are able to scale to high-dimensional images often get stuck in the face of uncertainty and stochasticity. So let us look at why is it the case that these methods are still inefficient, even though the reward is completely intrinsic. Our typical setup includes, given an image, you want to learn a policy, which outputs an action, that which you take the action, you go to next state. Now, most of the formulations make use of this transition of current image, action, and the next image. And they use this transition to generate an intrinsic reward. So one idea could be to learn a prediction model, where given the current image and the action, you predict the next image. And then you compute your prediction error, which is your intrinsic reward. Then your policy is optimized to explore the areas wherever prediction error is high. Now, this works very well in practice. However, for this objective to optimized, you have to take action in the real world to compute this xt plus 1. But the real world is black box. Environment is black box, so it's a very hard optimization problem. And hence, you have to rely on reinforce to optimize this objective altogether, which is fine in expectation, but very high variance operator in practice and takes millions of samples. Since the reward is completely intrinsic, can we do something better? So over here, we look at this model, but instead of learning one model, we build a number of these models. All right? Each of these models are trained in the same manner to minimize their respective error. However, we reformulate the notion of exploration from this prediction error to the disagreement of the output of these models. Then you use this objective to optimize the policy. So why is this a good metric, first of all? So wherever your agent's error is high, all the models will disagree on what the output is. So they will perform very similar when the environment is deterministic. So this approach performs as well as other methods when the environments are deterministic. So on the y-axis, you have reward. On the x-axis, you have number of frames. And the green curve is our method, and it compares favorably to all the previous best methods on Atari benchmark. But in the case of stochasticity, this model has an edge, because when the environment is noisy, all the models will go to the mean prediction, and their disagreement will drop, and the agent will get unstuck. So in the presence of stochastic scenarios, our method does well. So on the left, there is the environment is deterministic. On the right, the environment has noise. And our method, which is the green curve, performs same in both the cases, while the baseline drops. Now, one benefit of this approach is that in order to compute this disagreement, you don't actually have to act in the world to get xt plus 1. You can compute the disagreement of the output by simply taking variance of the outputs. Now, this equation does not contain any xt plus 1. So this does not depend on the environment directly. And you can optimize it in a differentiable manner. And you can rephrase this objective as a maximum likelihood estimation, where you first optimize the policy, first optimize the model using maximum likelihood, and then you train the policy through the model, again using maximum likelihood, using simple gradient descent. Now, this makes the process sample efficient, and hence we are able to apply this on a real robotic setup, where here's a robotic arm with a camera, and the setup is as follows. There are few objects in front of the robot, and we keep only 1 to 3 objects, so that it's very hard to touch the object randomly. And in this setup, when we run our method, in approximately 1,000 to 2,000 samples, our agent learns skills like pushing objects, picking them, placing them at other location. I cannot show video over here, but visit our website for the videos. So in summary, we propose a new formulation for exploration via disagreement, which performs similar to other methods in deterministic environments in simulation. It does not get stuck in the face of uncertainty. And finally, we propose a differentiable reformulation, which is able to scale to real robotic setups. All the code and everything is available online on the website. Please come to our poster number 39 today. Thank you.
Right, and our final spotlight talk of the session is called Pearl, Efficient Off-Policy Meta-Reinforcement Learning via Probabilistic Context Variables. Will be presented by Kate Rakelli.
Thank you. This is joint work with Auric Cho, along with Deirdre Quillen, Chelsea Finn, and Sergey Levin. So learning approaches have excelled in producing agents that are specialists, that is, good at one specific task. But in reality, we'd like our learning agents to be generalists, skilled at a variety of behaviors, and able to exploit the structure in the world to learn new tasks faster. For example, surfing, skateboarding, and sledding all involve balancing your body on a board while it moves. If an agent is already skilled at performing one of these sports, we'd like it to be able to learn another one more quickly. One way to formalize this problem is as meta-reinforcement learning. Consider now a quadruped agent navigating to goal regions shown as blue circles. Given a small amount of experience in a task with a new goal location, the agent should quickly adapt to solve it. And it learns to do this during meta-training, during which it learns to solve many related tasks. So once trained, adaptation to a new task is fast. But during meta-training, we must collect data from each of a number of training tasks, exacerbating the sample inefficiencies that plague RL. Existing meta-RL methods, such as ProMP, MAML, RL squared, rely on on-policy RL algorithms, which are incredibly data-hungry. To see just how sample inefficient these algorithms are, let's take a look at how they perform on some common meta-RL benchmarks. These are task distributions like a humanoid running in different directions, or the ant navigating to different goal locations. Here, we're looking at the average return of test tasks plotted against the number of training samples on a log scale. All of these methods require hundreds of millions of samples to learn a good policy. If we ran these algorithms on a real robot, that would translate to nearly 2 months of continuous training. And so we know that for single task RL, off-policy algorithms can be 10 to 100 times more sample efficient than their on-policy counterparts. If we could adapt them to the meta-learning setting, our training time could be reduced to about half a day, bringing meta-RL within reach of real robotic systems. So today, I'm going to present a method that achieves these results, shown in blue. Remember that the x-axis is in log scale, meaning that this method uses 20 to 100 times fewer samples than the baselines. It also often outperforms them. For example, it achieves twice the returns of the best baseline in the humanoid domain. We call it PEARL, probabilistic embeddings for actor-critic meta-RL. So how can we get these results? So one way to view adaptation in a new task is as a procedure for extracting task-relevant information from the experience the agent has seen so far. We call this experience context, and we call the extracted information Z. In this example, the context is a few trajectories of navigating around the plane, and Z should encode some notion of where the goal is. The agent must then know how to use Z to modify its behavior in order to complete the task. So meta-training then consists of 2 things. First, learning to summarize the context into the variable Z, and second, learning a policy that can act optimally according to the given Z. We implement this idea with an efficient off-policy algorithm, soft actor critic. The latent task variable Z is inferred from context via a neural network with parameters phi. Actor and critic take Z as an input in order to act according to the current task. Note that here we sampled 2 batches of data from the replay buffer, a context batch to infer Z, and a batch to train the actor and critic. The fact that our algorithm allows these batches to be separate is a key element in enabling off-policy learning. Please see our paper for more details. Rather than inferring a point estimate of the latent task variables, we can maintain a belief distribution over them. This belief represents our uncertainty about the current task, and we can make use of it to explore in a temporally extended manner via posterior sampling, also called Thompson sampling. During adaptation, we iteratively sample a Z, act according to it for a trajectory, and subsequently update our belief given the evidence. To see how this works, consider a robot navigating to different goal locations on the half circle, with rewards given only within a small radius of the goal, shown in blue. During meta-training, it learns a prior that goals always lie on the half circle. Given the new goal, shown in blue, it explores by taking a guess about the goal location and iteratively refines this guess over time as it collects more data, smoothly transitioning from exploration to exploitation. All right, in summary, we presented the first off-policy meta-RL algorithm. It's 20 to 100 times more sample efficient than previous algorithms, and it explores efficiently by maintaining a belief over the task and using posterior sampling. We're on arXiv, GitHub, and I wish the slide would show, but please come to our poster at number 40. Thank you.
Thanks, everyone. That's the end of the session.